engineer at Change. His hobbies include math, parenting, and magnets. And he's going to tell us about the irrationality of the square root of 2.
Hello. Okay, so I'm going to talk about the square root of 2, or a number when multiplied by itself gives us 2. And how I'd like you to think about this number is a distance of the hypotenuse where the base and the height are of a right angle triangle are 1. So this is the number line. And this can be thought of as distances from 0. So you have 1, 2, and I won't name them all, there's lots. So when we want to represent distances that exist between the integer points, we have fractions that are in the form of a over b. And we make infinitely many subdivisions. So in between 0 and 1, there are infinitely many subdivisions we create. So now if we have an infinitely many subdivisions, well, certainly we can represent any distance we want on this number line. Maybe. So we want to see which of these infinitely many fractions that we have created between 1 and 2 represents this square root of 2. And so we write this equation down and we see what kind of meaning we can derive from it. So you actually can't, spoiler alert, and we're going to use this thing called a proof by contradiction. It's when you assume a premise and then you do some number crunching and some algebra and you see that it leads to some kind of problem. So what we're going to assume is that a over b in this situation are in lowest terms, which I'll describe in a second. 1 second. Okay, so what is lowest terms? It's when you have a fraction and you can divide the top and the bottom by the same number and get a lower number. And so the thing to take away here is that an even over an even is never in lowest terms. And then we can talk about what is an even number. Well, an even number is like blah equals 2 times bleh, whatever those things are. So 8 is an even number because it's 2 times 4. 9 is not an even number because it's not. Okay, so we have a over b equals the square root of 2, and we can square both sides, and we can distribute the square sign in the fraction. Then we can move the b squared onto the other side, and we have the fact that a squared is even because it's 2 times something else. We don't care. And remember this thing on the top right here, we're going to need it for later. So now, if a squared is even, then a is even. And that's because there's 2 options for a. It's either odd or even. If it's odd, an odd times an odd is an odd, and an even times an even is an even. So that means that a is even. Now, if a is even, we say that a equals 2k for some k. And then we go back to our formula that we had on the previous slide. So then what can we do here? Well, we can replace a equals 2k down into this formula, and then we can square 2k, so we get 4k squared. Then the 2 and 4 cancel out, and we get b squared equals 2k squared. So b squared is even. And so, since b squared is even, b is even by the same logic as before. So, but 1 second. In our initial assumption, we had that a over b was in lowest terms. Now we've concluded that a is even and b is even, and that leads to a contradiction. We can't have that. So a over b is not in lowest terms, just by wrangling the formula around. And so I'm going to talk about the implications. So the statement does not make sense. There isn't a fraction that represents the square root of 2. So even though we've subdivided the space in between 1 and 2 infinitely, there are still cracks, there are gaps in between our infinite subdivisions. So these are called real numbers or irrational numbers. and fractions are rational numbers. So just to conclude, that in between the subdivisions, there are infinitely more numbers.